Number 1 gives us 6 different functions, and it asks us to classify each as linear, exponential, or neither. So let's think about what a linear function looks like. So remember that a linear function is going to be a function in the form of a starting value plus some number times x. Okay, so it's going to be in this form, b plus ax. And an exponential function is in the form of an initial value times some growth factor to the x power. And then you could have stuff added or subtracted outside of it as well if you wanted. So the main thing to notice in these is that in a linear, you have a number times your variable. And in an exponential, your variable is in the exponent. So for part A, we just see a number times the variable. That means that this is linear. In B, we see that the variable is in the exponent. So then this is going to be exponential. In function C, we don't see either of these things happening. It doesn't say 3 times x, and it doesn't say 3 to the x power. So this is going to be neither. This is actually a cubic function when we have the variable brought to the third power. Function D has a number plus 3 times x. So again, we are multiplying by our variable, right? So that's going to be in the form of a linear function. E has a number times 3 to the x power. So again, our variable is in the exponent. So then this is going to be exponential. And then part F has a number times 3x. And so we could really simplify this one and say that it's, 27x if we wanted to. And again, that one's just multiplying by the variable. So then this one is just going to be linear. Number 2, here are 4 equations defining 4 different functions, a, b, c, and d. List them in order of increasing rate of change. So that means to start with the one that grows the slowest up to the one that grows the quickest. So when we're talking rate of change, that's the number times the variable. So all of these are linear. So we're looking at the slope of each one. So in A, it's 5. In B, it's 3. In C, it's 1. And in D, it's 4. So that number right in front of the variable multiplied by the variable. So the larger the number, the steeper the slope, or the steeper the rate of change. So that means that our slowest growing one is going to be C of x with the rate of change of 1. Then we're going to go to 3. So that's B of x. Then we're going to go to a rate of change of 4, which is in D of x. And then finally our steepest, which is A of x. Number 3, function f is defined by 3x plus 5, and g is defined by 1.1 to the x power. So we have a linear function, and we have an exponential function. It wants us to complete the table with the values for f of x and g of x and round to 2 decimal places. So you can just type these into your calculator. So f of x, if we plug in 1, we are going to get back 8. If we plug in 5, we're going to get back 20. If we plug in 10, we're going to get 35. And if we plug in 20, we're going to get 65. So we're just doing 3 times x and then adding 5. For the exponential function, we're going to do 1.1 to the x power. So 1.1 to the first is just 1.1. 1.1 to the fifth is 1.61. 1.1 to the 10th is approximately 2.59. And 1.1 to the 20th is approximately 6.73. So then part B asks us, which one do we think is growing faster, and explain your reasoning. So you might know that just overall that a linear function, right, is going to be like this. It's going to constantly grow at the same rate. And then an exponential is going to grow slow in the beginning, and then it starts to get really fast. So for these values, if we take and we do 65 divided by 8, so where we ended up at 20 divided by where we started, we get like that 65 is 8.1 times faster. Or if we did 6.73 divided by 1.1, we end up with that one's about 6.11 times bigger. So it appears, for these values that f of x is growing faster. So on this domain, it shows that f is growing faster. Now, if we zoom out of that function and we look at a wider domain, more x values, then that's going to change. So this part C says, use technology to create graphs representing f and g. What graphing window do you have to use to see the value where g becomes greater than f? So we see that these orange values are significantly higher than the blue values. But because of the way an exponential grows, that it starts slow, but then it starts to get faster, we know it'll overtake the f graph. So when is that going to happen? So if we graph these, we see this window here, or we see this graph here. And so I just graphed mine from x's 0 to 60. And then I did y values 0 to 200, and that should say y, not x. Okay, so I did my y values. Let me do it this way. 0 to 200, and then you can see when they cross. So it's going to be at 54, about 50, 53.6 is when they're going to be the same. So anything above that is when the linear function will surpass it. And I kind of did this poorly because on here it looks like this is the blue graph. So I probably should have done this as blue to match the graph. And then this as, orange to match, so we can kind of see. But this is the linear one. And then when does the exponential one surpass it? And that's at about 53. Number 4, functions m and n are given by m of x equals 1.05 to the x and n of x equals 5/8 x. As x increases from 0, which function reaches 30 first and which function reaches 100 first? So I would graph this so you can look at it. So we're looking at when does it reach 30? Okay, so for this first one, we were looking at 30. And this is when does the function equal 30? And for this second one, we're looking for when it equals 100. So then you want to be looking at this output, right? So we want to find 30. So which function hits 30 first? Well, that's going to be n of x, right? Because it hits it at around like 46, but it definitely hits it first. So this is n of x. And which function hits 100 first? So if we go up to 100, so which function hits 100 first? And we can see that it's this one because the other one doesn't hit it till off the screen. So that one is m of x. Number 5, functions f and g are defined by these two functions, one being f of x being linear and g of x being exponential. Which function eventually grows faster? So eventually grows faster. Remember, the linear will stay the same rate of change. It's going to grow at a constant rate of 8. The exponential is the one that will start slow and then it will start to get faster and faster. So this is going to be g of x, and we know this because it's exponential. And you could say that more if you wanted, because it's exponential, so we know it's going to start like it doesn't have a constant rate of change. It's going to start slow and then get faster. Even drawing a picture of it. Explain why the graphs of f and g will meet for a positive value of x. So if we think about kind of where these graphs, what these graphs are doing, how they're starting and then how they're moving. So we know that this f function starts at 33. Okay, so let's pretend 33 is here. And then it grows at a constant rate of 8, right? So this is what the linear function graph will do. Then the exponential graph is starting at 2. So it's starting way down here, but then it's slowly growing, and then all of a sudden it's going to grow faster and faster, and it's going to overtake that f graph. So we know that this will happen because f of x starts above. So it starts above g of x, and then g of x will get, I don't know the right way to say it. Let's think. So then g of x will get steeper or start growing faster, will eventually grow faster to overtake or become larger than f of x. So since, right here, g of x is starting lower, and then it's going to grow faster at some point, while f of x just keeps staying constant. So combine kind of those, the picture and the words idea. Number 6, a line segment of length L is scaled by a factor of 1.5 to produce segment M. The new segment is then scaled by 1.5 again to give the length of N. What scale factor takes us from L to N? So I'm gonna write this out. So the L function, okay, so a line segment length L is scaled by 1.5 to produce M. So we know that M equals 1.5 times L. That's what scaling means multiplying it. Then it says the new segment, okay, is then scaled. So M is then scaled by 1.5 to get N. So this is the new segment, right? M is the new segment. So we're taking our N segment equals 1.5 times N. So now if we looked at substituting this in, okay, so here's really our M segment, right? It was just our L times 1.5. So if we put that in here, if we substitute it in for M, we actually get that N equals 1.5 times 1.5 L. And so if we look at this without the parentheses, we get 1.5 times 1.5 times L. And 1.5 times 1.5, we could write it as 1.5 squared times L. So this is our scale factor that takes us from the original L all the way to N. We take it times 1.5 squared. Or you could say 2.25. So we took L, we multiplied it by 1.5 to get our new segment. Then we multiplied that new segment by 1.5 again. So we really, again, got L times 1.5 squared, or you could multiply that out and put it as 2.25 for your scale factor. Number 7, a couple needs to get a loan of $5,000 and has to choose between 3 options. Option A is 2.25% quarterly. Option B is 3% compounded every 4 months. Option C is 4.5% compounded semi-annually. If they make no payments for 5 years, which option gives them the least amount owed? Okay, so the least amount owed, because this is a loan, not in a bank account. Use a mathematical model for each option to explain your choice. Okay, so in this one, they are giving us the interest rate that is compounded in each situation, right? So it doesn't say that this is the annual interest rate. It says this is the interest rate that they're compounding quarterly. So when we do the initial loan value, then we're going to do times 1 plus just this percent as a decimal. So so this is really 2.25%. So when we divide that by 100, we get 0.0225. And then this is being compounded quarterly, which means 4 times a year. So then we're going to do 4 times per year. And remember, this is for 5 years. So we don't need to divide up this interest rate because they've already done that for us since they told us this is the compounded interest rate. So now type that into your calculator and you get $7,802.55. So that's for option A. Option B has us compounding every 4 months. So remember, there's 12 months in the year. So if we compound every 4 months, that means we're going to be compounding it 3 times in the year. So this one, again, they gave us the compounding interest rate. So we'll change 3% to a decimal. And then we're going to do this 3 times per year for 5 years. So then when we type that into our calculator, we are going to get $7,789.84 for that balance for the loan. Then on the final one, we've got 4.5% interest compounded semi-annually. This means twice in the year. So we're going to have that $5,000 initial deposit. Then we're going to have 4% as a decimal, which is 0.045, compounding 2 times per year for 5 years. So then we'll type this into our calculator and we get $7,764.85 for that option. So then you're looking for which of those options is the least. And so we've got 7,800 versus 77. So it's not that one. This is 77.89 and this one is 77.64. So option C gives the lowest balance. Okay, then number 8, here are graphs of 5 absolute value functions match the graph and equation that represent the same function. So we see that these are just moving left, right, up, and down from the parent function. So here's our parent function. The parent function is going to start at the origin. So this one is our parent function. So this one is equation A. Then the rest of these just move from the parent function. So when you have a number on the inside, it moves opposite of what it looks like, but left or right. So a negative on your graph, right? A negative x would move to the left. but when it's inside the function, it does opposite of what you think. So this one's actually going to be to the right 5 units. Okay, so we want to see which one takes and moves this graph to the right 5 units. And we see that here at number 1, if we go from 0, 0, and we go to the right 5, that's this graph. So graph number 1 goes with equation B. Then C has the -5 outside of the function. So when it's outside of your function, then it impacts the range, meaning it goes up or down. And it does exactly what you think it would do. So a minus on the outside is going to go down 5 because your y values go up and down. So now we're going to look for the graph from this parent function that goes down 5 units. Okay, so we're looking for one like that. And we see it over here at number 5, graph 5 down 5 units. And that is with equation C. So then D again has the number inside of the function. So that's going to impact the domain opposite of what you think. So a +5 is actually going to move it left 5 units. So from here, we're going to move to the left 5 units. And we see that in graph 4. So then this is D, and then that leaves number 2 to be E, which it is because that 5 is outside of the function, which moves it up 5 units. Oops, no, those got attached. Okay, so then this one would go, oops. Okay, so this one would go up 5, right? And then give you graph E.